Hi, I'm Spring, and this is my Lab 2 video for Physics 2211. So the purpose of this second lab is to analyze the motion of a falling object, which is a tennis ball, and create a computational model that predicts its motion based on the observed data. However, I will be discussing two cases, which is a model with and without drag force or air resistance. Then I will conclude my lab by discussing any assumptions I made and answering concluding questions. In this lab, we will revisit some earlier concepts of Newton's second law from the first lab involving constant velocity. However, in this lab, I will explore changing velocity as a result of a non-zero net force acting on the same falling tennis ball. Both weight and drag force will act on it. So in the equation on the right-hand side involving net force, this will actually play a part in the experiment as opposed to the first lab where it equaled zero. Again, Newton's second law is also called the momentum principle because momentum is just mass times velocity, and rearranging the first equation above results in the last one. And then here's the tracker video of me dropping a tennis ball, and then the data is on the right. Okay, cool. So here's all of the code for our case without drag force. And when we run this program, it just gives us a ball going straight down. And then here is our code for our model with drag force. And when we run this program, you'll see that there's two arrows, one for drag force going up and then one for weight force going down. In these segments of code from the case of no drag force, where b equals 0, I have set g to be 9.8 and j hat to be 0, 1, 0 for the time duration until 0.633 seconds. It'll run this while loop with these equations below. And then in comparison, the code with drag force has b equals 0.003, which took several attempts to match this predicted final y value to the observed one, which we'll see on the next slide. Since drag force is included, I had to change the net force equation to be a quadratic relationship to speed. And so here is my data in Excel with the observed on the left and predicted with drag force on the right. I have the first two graphs shown here of just the blue and orange data corresponding to the colors. And then here's all three data sets on one graph. Notice that the final y positions of the green and blue graphs are roughly equal, although the time on the x-axis is different. Although they end at the same spot, the data in between differs, meaning there was some error in both estimating b in GlowScript and recording the tennis ball for the observed data. In the actual dropping of the tennis ball, I omitted many factors like the role of the texture of the tennis ball, which has to do with the drag force, and I also did not film it perfectly perpendicularly. Also, it is nearly impossible to get b to be in the exact same y position in GlowScript. As for the orange graph, it predicts that the tennis ball will fall much faster than the first two graphs, which makes sense because it doesn't account for the opposing drag force. Therefore, it's a less accurate prediction for objects falling through the air, but good for a vacuum with no drag force. And then here are conclusions and assumptions. So what does it mean? Terminal velocity is the maximum speed that an object can attain while falling through a fluid, which is air in this case. Terminal velocity is reached when drag force is equal to the force of gravity. This means that the net force is 0 and the object will have a constant velocity and no acceleration. The model with drag force predicts this with a curve that approaches an asymptote that is at the y value representing the terminal velocity. The model without drag force is unable to do so for obvious reasons. However, the second model fails to include important values to truly calculate terminal velocity. There is no inclusion of the surface properties of the tennis ball, its hollowness, or whether I unintentionally push the tennis ball down with some force instead of just dropping it. So then this leads to the next point of our what if. What if I threw the ball downwards, which would add more downward force initially? Although the velocity of the tennis ball would be greater in this case, it would eventually slow down and reach the same value even if it takes more time for it to do so. So that means the terminal velocity would be the same. This idea is best represented by comparing these two graphs of velocity as a function of time. Without drag force, the graph is a straight line that seems to just reach 0. However, with drag force, the graph is a concave curve that approaches an asymptote of around -4 meters per second. Although the object will never actually reach this terminal velocity, it is constant for that object even if there are external forces like throwing it downwards.